Hello students, I'm Mr. Ruffler, a high school chemistry teacher, and welcome to the channel. In this series, we're walking through the new June 2026 Chemistry Regents exam, cluster by cluster. This is the 10th video of the series where we're going to tackle the all about aluminum cluster. If you're looking for a different cluster, check the playlist in the description below where you'll find step-by-step walkthroughs of the rest of the exam. Let's get started. So our first step here is going to be to read the entire cluster. There's not too much information here, so let's try and understand what it's telling us. The United States uses over 80 billion aluminum cans per year. The aluminum is extracted from bauxite, an ore that contains various aluminum compounds. Figure 1 shows abundance of some elements in Earth's crust. The properties of aluminum, such as its malleability, ductility, low density, thermal and electrical conductivity, and resistance to corrosion are desirable for many consumer compounds. Figure 2 provides some examples of uses of aluminum. There's a lot of information here that we'll probably have to come back to. Question 42 asks, which statement describes how the structure of aluminum metal supports its function? Choice 1, aluminum has tightly packed atoms that allow for high density in airplane parts. Aluminum has loosely packed atoms, then it says aluminum has mobile electrons for both, and that contributes to conductivity, either good or poor. All right, so there's a few things we need to assess from the chart. So let's try and eliminate some of these answer choices. Choice 1 says that aluminum has tightly packed atoms that allow for high density in airplane parts. Let's go see if it says anything about airplane parts here. So if we look, it says that we have transport as a use and parts for airplanes, buses, ships, and trains. Let's see if it says anything about density. Well, it says that the properties of aluminum are malleability, ductility, and low density. All right, this answer choice is saying that aluminum has high density, so we can eliminate it. All right. Choice 2 says aluminum has loosely packed atoms that allow for high density in bicycle parts. Again, the passage just said that it has low density, so we're going to eliminate that choice. Choice 3 says aluminum has mobile electrons that allow for poor conductivity in pots and pans. And then choice 4 says it has mobile electrons that allow for good conductivity. To answer this, you really need to know how mobile electrons work. Assume here I have a metallic substance, right? Metallic bonding is characteristic with mobile electrons, okay? What that means is here you have the atoms minus their one valence electron, or however many valence electrons they have. In this case, I just drew one per atom. And within metallic bonding, those valence electrons are free to move throughout the substance, and this is why metallic substances conduct. So all of these mobile electrons can really move, they delocalize from their atom, and the moving charges, the moving electrons, the mobile electrons, are what allows for the conductivity, right? Anytime you have something that's charged that can move, whether that be a mobile ion in ionic aqueous solutions or mobile electrons in metallic substances, that's going to allow for very good conductivity. Hello, right, students. I'm Mr. Ruffler. Knowing that mobile electrons allows for good conductivity is going to mean that we're going to choose choice 4. All right, question 43 says, predict the outcome of a reaction between aluminum and the second most abundant element in Earth's crust by writing the chemical formula. All right, so we have to go back to the passage again. So in figure 1, it tells us the abundance by mass in Earth's crust, and we want the second most abundant element. So oxygen is going to be the first because it has 46.1% abundance. Silicon is going to be the second, and aluminum is going to be the third. So the second most abundant element is going to be silicon. So we want to figure out what the reaction between aluminum and silicon is going to yield. We're going to have to crisscross this. So let's go to our periodic table and look for aluminum and silicon. Okay, right here is aluminum and here is silicon. So what we need to do is figure out the charges that these ions are going to have. Right? To do that, we need to know valence electrons. So this is 1, 2, 3, 4, 5, 6, 7, and 8. So then the charge, which we'll write in blue, hydrogen is a little special, but typically +1, this beryllium, and that group will be +2. Since group 13 has 3 valence electrons, if it loses them, it's +3. 14 is either +3 or -4. Then we get to group 15. So if we have 5, we're probably going to gain 3 electrons. So it'll be -3. Group 16 will gain 2 for -2. 17 will gain 1 for -1. And then the noble gases are typically 0. So with that information, we know that aluminum will be +3. And if aluminum is going to be the cation, the positive ion, we're going to assume that silicone is going to be the anion. So I'm going to say -4 for silicone. So we have to crisscross aluminum, which is +3, with silicone, which is -4. Crisscrossing this, we will get Al4 Si3 for our credited answer. Okay, moving along. In the mid-1800s, the small available quantities of purified aluminum were more costly than gold. The isolation of elemental aluminum required large amounts of energy and time at a substantial cost. Around 1888, the first low-cost, large-scale electrolysis method for extracting pure aluminum from aluminum oxide was developed. This method is known as the Hall-Héroult process. Figure 3 shows the electrolytic cell of the Hall-Héroult process. Right, I'm just going to underline electrolytic cell because that's important to distinguish between electrolytic, which is electric to chemical energy, from voltaic, which is chemical to electric. So let's just write that down. This is electric to chemical. That means that we must have an external power source that's powering a non-spontaneous reaction. Okay, then below it says equation 1 represents the half reaction that takes place at the carbon anode. Right? If carbon is at the anode, then we also can remember anox, red cat, and think, well, carbon is going to be oxidized. All right, so that's our chemistry component of this passage. So moving along. Which row identifies the product that are formed at each electrode, being anode and cathode, during electrolysis? When we read the passage told us that carbon is formed at the anode, so we know that the anode is the site of oxidation. If we want to think about the product that's going to be formed at the anode, we want to look at this half reaction. So at the anode, we're oxidizing carbon to form carbon dioxide and 4 electrons. So the product that's formed at the anode, the product of the oxidation, is going to be CO2. Right off the bat, we can eliminate row 1 and row 3 because they don't have CO2 being formed at the anode. Then we want to think about what's going to be formed at the cathode. If we go back to the passage, the entire point of this Hall-Héroult process is to make aluminum. And if we're making aluminum, we're going to be making the elemental form, which is Al0. In the passage, what it says we're doing is we are extracting pure aluminum from aluminum oxide, Al2O3. If we think about the oxidation states for this Al2O3, for aluminum it's going to be +3, and for oxygen it's going to be -2. So what we're doing at the cathode is we're taking Al +3, we're adding 3 electrons, and then we're forming elemental aluminum, which is Al0. Right? Again, recall that in elemental form, you're just going to have an oxidation state of 0. So this is going to be the product at the cathode. All right, so at the cathode, if we're not writing the oxidation state, it's implied that it's 0. So we're going to pick choice number 2. Question 45 says, which row provides evidence to support the claim that the Hall-Héroult process involves a transfer of electrons as an energy conversion occurs within the system? So we have a redox reaction, which we know is just a transfer of electrons to something that's oxidized, from something that's oxidized to something that's going to be reduced. The passage states that carbon is oxidized. So if carbon is oxidized, that means carbon will be the source of electrons. So if we're looking at this criteria here, source of electrons, it can't be oxygen minus 2. So we're going to get rid of rows 1 and 4. In the last question, we figured out that the Al plus 3 is what gets reduced because we have Al plus 3 electrons forming Al0. Okay, so if this is our reduction reaction, that's the aluminum half reaction, that is corresponding with this equation. So we can eliminate choice 2. But if we want to assess the other criteria, remember back in the passage we underlined that figure 3 shows an electrolytic cell, and we said that electrolytic cells have a conversion of electric to chemical energy. This matches up for choice 3. Right here for choice 2, chemical to electric, that is describing a voltaic cell, which this is not. So our answer is going to be choice 3. So that's it for this cluster. If you found the video helpful, be sure to like the video and subscribe for more walkthroughs. When you're ready, you can access the playlist in the description below and move on to the very final cluster of this Regents exam. Happy studying!